So today we talk about radioactivity, our last chapter in a series of somewhere around 18 chapters that deal with 4 units, and this is the last chapter in our last unit, radioactivity. Radioactivity means activity from afar. Activity from afar. If you see that symbol, well, you should be able to know that and distinguish that whatever is behind that symbol should be radioactive. Okay? The story about radioactivity goes as such. In 1897, a merchant was in southern Pakistan. He found a rock, an intriguing rock. It was uranium oxide. And what was weird about that rock was it was very small, yet very heavy. Okay, heavy, somewhere around 13 kilos. And he found it intriguing. And he said, okay, I'll take it to this guy and sell it to him. Henri Becquerel. And he did. He flew to France, or he went to France. He didn't fly back then. He went to France and then he sold that to this guy, Henri Becquerel. He took it, placed it in his lab, and this guy, as a physicist, performed experiments. And he wanted to just take a photo of a certain experiment. So he took that cellulose film, those white films they insert into the camera obscura they used to go under, and cover themselves with this black sheet and take a photo. He found that film to be ruined, to be black. Okay, so he threw it away and tried to get another one. He found them all blackened. So he threw them away. He went and bought a new set of films and performed this experiment. 2 weeks later, according to the biography of Henri Becquerel, he wanted to perform another experiment. He took in one of the new films he has bought, only to find it blackened again. And then he started wondering what had happened. What had happened over there, only to find that, or to discover that this rock he has found, okay, from afar, that's the radio, from afar was able to ruin his films. So to ruin his films, that was the activity from afar. Something was going on from that rock all over to those films and ruined them. So he placed them away from his lab for like 2 months, a month and a half, and then he reintroduced them to the lab only to find this phenomenon again. So he was sure that those rocks were emitting something which is invisible to us, unheard of, we can't feel it, and that he called, my friends, radioactivity. Okay? So, an introduction to whatever we've been taught so far in the previous chapters is, first we deal with nuclides. A nuclide is a set of elements just like lithium-37, just like helium-24, with the number of protons being this, and this being the number of neutrons and protons. So for example, helium has 2 protons and 2 neutrons. Alright? And isotopes, when we talk about isotopes, we would be dealing with elements having the same atomic number but different atomic mass. So same Z but different A's, or different number of neutrons. When we deal with radio elements are radioactive elements, just like uranium, plutonium, polonium, thorium, einsteinium, lutetium, radium, all those are radioactive elements. Okay? So let's start then. Excuse me. Radioactivity, as we've said, it's activity from far. It's whenever an element spontaneously transforms into another element. For example, uranium transforms into thorium and an alpha particle, this. So one element changes into another element with the emission of particles as such, or radiation. Sometimes it does it both. Okay? So again, radioactivity is the spontaneous transformation of one element into another with the emission of particles / or radiation. Both of them might be obtained. Okay, now if you take a look at this video and this video, it will play in a while, I hope so. We would be able to see, okay, as I take a still image, we'd be able to see particles leaving this uranium oxide over here in a cloud chamber. You'd be able to see swarms of and sways of shooting particles in this cloud chamber. That is a video showing, as I'll post it separately, showing particles being emitted from that uranium oxide. The only problem with those particles is they're silent, they're undetectable, they're super silent, they cannot be seen, they're invisible, odorless, tasteless, you can't even feel them, and so suddenly you'll just fall dead. Okay, just to give you a clear idea of what's happening, this is Fukushima, 10 years ago, nearly 10 years ago. Fukushima, a power plant, nuclear power plant in Japan, underwent a seismic activity of somewhere around, it was, I think, the highest, 7 Richter, I think, or 8 Richter, and leakage took place in that nuclear power plant. No meltdown was observed. And the activity back then was 10 power 17 becquerel. 10 power 17 becquerels, it means 10 power 17 atoms being emitted every second. Imagine that local number, imagine that, it's a humongous number. It's 10 power 17 atoms per second. So 100,000 million atoms every second were being sent into water. They had to cool it down by salt water. And take a look at this. 5,000 tons all over shore were swept away of dead fish poisoned by radioactivity. Chernobyl, 1986. Ukraine, part of the USSR back then. The temperature of the 4 reactors, one of those 4 reactors in this power plant, was overrun until 1,000 degrees and kept on increasing until the nuclear power plant melted down. As it melted down, it exploded. As it exploded, it sent 10 power 19 becquerel of atoms into the atmosphere of all surrounding countries. And one of those countries is Denmark, which is somewhere around 600 kilometers away. So radiation was carried to Denmark. And that activity is also humongous. It's 10 million atoms per second. 10 million atoms per second. Imagine that number. It's unfathomable. We cannot think of it. Okay? Hiroshima, at the end of World War II, when the United States dropped the bomb, the fat boy on Hiroshima. Take a look at the activity. It's somewhere around 1021 atoms per second. We're talking about humongous number of disintegrations. Atoms per second, which we cannot see. Okay? So 300,000 people were dead just of the blast, and God knows how many of the radiation. And if you don't die, you will develop severe consequences. Probably burns, catalytic burns, genetic mutation if nothing happens to you. Okay, so we will see some of those images later on. Now we agreed that radioactivity is the transformation of one element into another with the emission of particles and radiation. To figure out those particles and radiation, this table, which you need to memorize, and I'll show you a very quick way of memorizing all of those with all of those characteristics. Okay? Alpha, for example, this is the symbol of alpha, and we denote it by this. Okay? Because we're going to use those too much, you'd be able to memorize all of those. Okay? Alpha, positron or beta positive. electron or beta negative, neutron, proton, neutrino, antineutrino, and gamma. Okay? Now, how will we be able to memorize all of this? If I tell you alpha He24, what is the nature of alpha? Particle. What's the nature of beta positive? Particle. What's the nature of beta negative? Particle. If you take a look, all of those are particles except for gamma. Gamma is electromagnetic radiation. Only gamma is electromagnetic radiation. Okay? Now, take a look at the charge. To figure out the charge, take a look at that number over here. This is positive. Take a look at that number over here. It's positive. At that number over here, negative. What's the charge of a neutron? It's neutral. What's the charge of a proton? It's positive. The charge of a neutrino, antineutrino, or gamma, it's neutral. They're all neutral. Okay? Now, let's take a look at the mass. Anything that is 0 over here is light. 0, light. 1, heavy. Not 0, it means heavy. 1, heavy. 0, light. 0, light. 4, not 0, heavy. Okay? Anything that goes with a 0 is light. Anything that goes with heavy is not a 0. Alright? Now, penetrating power. If the mass is heavy, then it has a low penetrating power. If the mass is light, then it has a high penetrating power. So, if you take a look at this electron, it's negatively charged. 0, it means it's light. If it's light, it has a high penetrating power. And its speed, this is the only bit which you have to memorize. Gamma, 0, 0, it's neutral, it's massless, since it's electromagnetic radiation. It has a very high penetrating power, and it travels with the speed of light. Now, the penetrating power, if you take a look, alpha is stopped by a piece of paper, while beta pierces through this paper, but it's stopped with aluminum. Okay? While gamma, which is the most dangerous, if you place your hand, or if you hide behind a lead wall of thickness 1 meter, and still you'd find some of those gamma are able to just penetrate that lead wall, which makes the constituents of the door of a nuclear shelter. Okay? And since those particles are charged, they are affected by electric fields and magnetic fields. That's a magnetic field, and that's an electric field over here, and they are swayed one side or the other, or if they are neutral, magnetic fields and electric fields wouldn't be able to affect them. Now we talk about natural and artificial reactions. Natural and artificial reactions. Let's pause for a while. Now we proceed to natural and artificial reactions. Okay? Natural reactions are reactions that are spontaneous. They happen all by themselves. As you take a look over here, I need to activate my pen again. Carbon all by itself has disintegrated and changed into nitrogen. Radium all by itself has disintegrated into radon. So you see nothing added over here. So those are natural reactions. While artificial or provoked or stimulated reactions, if you take a look over here, there must be external factors. Uranium, not all by itself, disintegrated into strontium and xenon. We bombarded it by a neutron. Aluminum, not all by itself, disintegrated into phosphorus. We must have added an external factor, alpha in this case over here. So not all by themselves. Okay, you see external factors being added. This is how we distinguish between artificial and natural reactions. Now, Soddy's laws are the laws of conservation of mass and the laws of conservation of charge number. How do you figure this out, for example? How could we have told that this is alpha? Conservation, Soddy's law, conservation of mass before 234, mass after 23 plus you see this. So this must have been 4. So to solve that, we say Soddy's laws, 234 equals 230 plus A. So that must mean A is 4. And now law of conservation of charge number, 92 equals to 90 plus Z. This is our unknown Z and A. So Z would be 2. And now we go search which element or which particle has a 2 and 4, and that is nothing but alpha, which we denote by HE, 2, 4. Those are called Soddy's laws. Now, as we proceed to alpha emitters, beta emitters, gamma emitters, and so on, how to distinguish and what does that mean between elements that are alpha emitters and elements that are beta and gamma emitters and so on. An alpha emitter is an element that decays emitting alpha. For example, uranium is an alpha emitter. If we see alpha, then it emits alpha. Over here, if you calculate A, 226, 222, that must mean A is 4. 88, 86, that must mean Z is 2. So this is alpha. So radium must be an alpha emitter. Okay? And to figure this out, take a look at the parent nucleus, and this is the daughter nucleus. It must have lost 2 protons and 2 neutrons. XA has become A-4 emitting alpha. And we find that nearly, almost always, gamma radiation accompany alpha emitters. So almost always we could see gamma over here. Almost always we could see gamma over here, unless we're told otherwise. Now, beta negative emitters are nuclear emitters that, as carbon, that emit and disintegrating into whatever, and they emit beta negative. Beta negative is E-10, and we notice that almost always antineutrinos accompany electrons. Okay, so they are inseparable. So that's an antineutrino with it. Okay, beta negative emitters should be elements rich with neutrons, just like carbon. It has 6 protons and 8 neutrons. In this case, it would be able to emit a beta negative particles. And this is the disintegration of beta negative. A neutron decomposes into a proton and an electron and antineutrino. Okay? Take a look at this summative reaction over here. It explains it. Take a look as it's balanced. A neutron disintegrates into a proton. 1, 1. But by doing so, we need to cancel that one and thus emitting an electron. Now, beta positive emitters are elements that decay emitting beta positive. Elements that decay emitting beta positive. Okay? But as they do so, electrons are accompanied by neutrinos. Almost always, beta positive are accompanied with neutrinos. Okay, and that's the general equation of beta positive or positron decay. A positron would disintegrate into a neutron. 1, 1. So these laws, law of conservation of charge number, 1, 0. So we must have a 1 over here, and that is our positron. Gamma emitters. Now, gamma emitters, gamma are electromagnetic radiations. They are emitted whenever an atom is de-excited, whenever an electron jumps from a high energy level to a lower energy level. We denote by star over here as uranium in the excited state. As it jumps to uranium in the de-excited state, it emits that gamma. Plutonium in the excited state, as it jumps to plutonium in the de-excited state, it releases gamma radiation. Okay. As for activity, we've discussed this towards the beginning of this chapter. It's the number of disintegrations emitted per second. An atom per second or disintegration per second is a becquerel. A becquerel is a very small unit of energy, of radiation. So we deal with the Curie. 1 Curie is 3.7 times 10 power 10 becquerel. That's a more suitable and convenient unit. When we go to half-life, the definition of a half-life is the time taken by radio element to decay or lose half of its initial mass. Those are the technical words that should be present. Half-life is the time taken by an element to decay half of its initial mass. For example, if I start with 100 grams, after one half-life I end up having 50. After another half-life I end up having 25. After another half-life I end up having 12.5. So with each half-life you just divide by 2, and this would be the decay curve of either of those elements, anything you wish. If you start with 100, after one half-life, let's assume that the half-life is 1 over here, you would end up having 50. After another half-life you'd end up having 25. After another half-life you'd end up having 12.5, and it keeps on going until it dies down in such an exponential fit. The activity is the exact opposite of the half-life. The activity is how fast would a radio element decays. Alright? And those are the equations of decay that govern all of whatever we've talked about. Okay? With m, the mass, being m0, the initial mass, over 2 power t over t, or even n equals to n0 over 2 power t over t, or even n equals n0 over 2 power t over t. Either one of those equations. We'll be dealing with examples on each one of those to figure out what they mean and what they stand for. Alright? Now, this page I'll be using to explain some of those equations. For example, let's assume you have uranium, a sample of uranium that contains 200 grams of uranium. Okay, let's assume that the half-life is whatever, 10 years. Alright, can you calculate the mass left after a month? And that month would be 30 days. You have several ways to attain that, many ways. The first way would be the easiest way. You start with 200 grams, and after 10 years, which is one half-life, you'd end up with 100 grams. And after another 10 years, you'd end up with half of that amount, 50 grams. And after another 10 years, you'd end up with 25 grams. So the mass left is 25 grams. And the mass disintegrated is this minus that. Now the second way would be an easy way also. They're all easy. The mass left is the initial mass over 2 power t over t. The initial mass is 200. 2 power t, the time taken, we said it's 30 days. The half-life is years. So that would be 200 over 2 power 3, which is 200 over 8, and that would be 25 grams. Once again, so the mass left is 200 grams. The third way would be, if you take a look at that formula, this formula, with lambda being ln 2 over t, m, the mass left, is m0 e power minus lambda t. So it's m0, which is 200, e power minus lambda, and t is, in this case, 30. All we care about is lambda. How do we figure out lambda? Lambda is ln 2 over t, so it's ln 2 over 10. So coming over here, that would be minus ln 2 over 10 times 30. If you do the math, that would be 25 grams. And a fourth way, a long way, but an easy way, you just plot this axis, the mass, and this axis, the time, and you have 10, you have 20, and you have 30, and 40 days, and so on. And the mass, you start with 200 at t equals 0. After 10 years, you'd end up with half of that, which is 100. After 20 years, half of that, which is 50. After 30 years, half of that, and you notice the curve is whatever we've seen before, and then all you have to do is go grid in your answer. After 30 years, the answer would be 25 grams. So here you have 4 ways to figure out the mass left, or you can replace the mass by number of atoms or number of moles, starting with this formula you know over here from previous years of chemistry. So it would be easy. Okay, now A, the activity, being now lambda times n. How come it's that? The activity, it's lambda times n, and the reason is lambda, which we call the decay constant, and we agreed that lambda is ln 2 over t. So that means it's per second, second minus 1, or so on. So the activity is, this is second minus 1, and this is atoms. So it becomes atoms per second, and this is nothing but becquerel, the activity, the number of disintegrations per second. And this, the activity is minus dn by dt, and it's obvious, clear reasons. The activity is the variation, the number of atoms decayed during a given time. So it's the number of variations of atoms per time, and that gives you the first equation over here if you replace A by lambda n, and it's negative. It's because of the decrease. If you take the slope of this decaying curve, it's the descent rate. Okay, let's leave that for another video on part 2 of the last chapter. Let's keep